Okay. Well, everyone, welcome to 182. Maybe I should go to the other slide here. And it's really nice to be back in person after a long time for me. I didn't teach in spring in person, so it's really great. So just starting off, like, what is this course and how do we feel about it? I thought I'd start with kind of acknowledging the most important thing, which is that, we're trying to study deep learning, and we don't know very much. This is a picture of my son with his Neural Networks for Babies book. I identify very much with sort of, his perspective on this material in terms of how I feel I understand it and how we all understand it, right? So one of the things that we're going to talk about in this class that's really important is what do we do in the context of something that we don't really understand that well? How do we kind of muddle through anyway? So, so that's, you can't hear the audio of him talking. You will feel like that many times and, want to say bye-bye to this material. But okay, so let's get into some how do I think about what the subject is? Okay. So I assume by now every single person in this audience has seen lots of news articles, press, heard about, seen videos on YouTube of all the cool things that people have accomplished using deep learning. I'm not going to waste your time showing you things that you can find online and just looking on the news. So how do we think about what it is? So fundamentally, when I think about the subject, deep learning is the use of simulated analog circuits to do information processing, where these analog circuits are defined by lots and lots of parameters. And instead of hand tuning those parameters and figuring out what exact values you want to use, you set those parameters using an optimization algorithm. And that optimization algorithm is driven by data. And that's kind of what you do in deep learning. Why do you call it deep? They're called deep because the information, when it comes from the input, flows through many circuit elements before I get to the output. This is like the circuit perspective on what deep learning is, and it kind of reflects what you do. Now, why are we doing all of this? Why are we building these circuits simulated? And why are we having this optimization algorithm set various parameters of them? The reason is we want the learn circuit. Learn circuit is a circuit after we set the parameters by the optimization algorithm to approximately capture whatever are the relevant patterns underlying the data so that we can use that circuit in interesting ways to solve problems involving new data. New data for which that pattern is presumably relevant. So that's what the subject is about. And it's about, so a lot of what we're going to talk about in the course is we're going to talk about different circuit architectures that are useful for different types of problems and that have different properties. So a lot of the main part of the class will be going over them. And then details about how do you deal with that circuit architecture, what's involved. Now there are also general principles that apply to different architectures. And you can use different architectures for different problems. All of that we'll go into later in the course. But this is what the subject is about. Now, there are many different hypotheses out there for why you need depth in the circuit. There is the belief that this is for allowing representation learning. There's some evidence for this. There's also a belief that this allows for different kinds of functions to be represented more efficiently. There's evidence for that. There's the belief that, no, it's more like a telescope, where you have lots of different lenses to bring the appropriate things into focus. You can't say the intermediate lens has some appropriate representation. It's like you're just trying to bring a pattern into focus. There's some evidence for that too. So we don't really understand a lot of what's going on, so I'm not going to try to claim a particular perspective here. As we go through the course, we will kind of engage with these mathematically, but I don't want to claim that we know more than we do. Okay, so what kind of class is this? Right? This is a specialized class. So what do I mean by that? In the Berkeley context, this is a chart of the Berkeley EECS curriculum that Ada Kapanu put in. You can find it online on HKM's website. So where is this class? This class is here. Okay? So the path that students are expected to sort of take to get here is start in the freshman year, 16A, 16B, 70, learn probability and optimization, take a general machine learning class, and then you are here. So why do we do this? Why do you need all this? Right? Hopefully the description has helped you understand this a little bit, why this is relevant. So I'm going to talk a little bit more about the preparation kind of in some detail. So let's just think about the different topics, subtopics of preparation that are needed. Hopefully people can see what I write here. Tell me if you can't. So as I described, the way that the subject works is kind of sitting at the heart of what's going on operationally is optimization. Did people see when I wrote optimization? People on that side? No? Okay, maybe we can raise this screen up. Hopefully it'll automatically turn off, or I don't care if it does or doesn't. So why do you need to know optimization? Because that's how you train these things. That's how you set these parameters. If you don't have an intuition and understanding of optimization, you're going to get lost in the optimization details and lose track of the deep learning details. So we're going to assume an understanding of optimization. Where do you learn optimization? In the Berkeley context, and here I'm speaking mostly to Berkeley undergrads, optimization ideas show up in A, 16B, 127, and a bit in 189. For the graduate students in the audience who might have learned in other schools, you can ask on the 282A ed if you're, what details of your background, and we can address that, what you need to know. But you need to know this stuff to understand. So now the next question that comes up is, what if you don't? Or what if you don't understand it well enough? For graduate students who have a lot of time to take more classes, who can sort of build up to it, who don't need necessarily this material right now, I would say take 127, 227A, and you'll be ready when it comes to the optimization material. If you don't have time to do that, we're not going to exercise all of the detail level in 127 and 227A. The most important stuff we're going to use is actually hit here. But so we're going to try to keep things as elementary as we can, but there's times when we're going to say something that you're not going to understand, so you have to be able to fill in that gap. So when we think about optimization, what do we, kind of in that mix, we have two components of it that are particularly important for us, because they also help us understand modeling, especially in the case of linear algebra. So linear algebra, critical background. Again, what are the classes that hit the relevant level of linear algebra? And there's review here, but this is not needed. Linear algebra here is sufficient for us. Why do we need linear algebra? It's not just because it's like the language we use. It's also because it allows us the ability to visualize certain things and to invoke geometry. So as we say, the big challenge in the subject is we don't understand what's going on pretty much beyond that baby level book. I mean, we do, but not that much beyond relative to where we need to be. So anything that helps us engage our intuition is very useful. And linear algebra with its geometry is extremely useful to help us engage our intuition. The other thing you need on the optimization side is vector calculus. Where is vector calculus engaged with? In the Berkeley curriculum. Math 53, Geek 16b, and in 127. 227. We're going to try to keep the vector calculus kind of, in terms of how much we have to engage with it symbolically, kind of manageable. A lot of stuff the computer will do behind the scenes for you, but you need to understand conceptually. So this is kind of like, we describe this as the optimization grouping of things you need to know. We need to know something else, too, to get to understand the material. And that's probability. Now, what's interesting is that probability didn't show up anywhere in that description that I read to you about what kind of deep learning is, right? And that's really interesting, right? Because it's when you're doing things, probability is often playing a role in the background of helping us think about it. So what do you need to know for probability? TS70 is like a very basic. It's not nearly enough. What you need is the probability in EECS 126 or that one. That's the background we're going to actually count on here. So probability gives us a strategic language in which we can think about uncertainty. And uncertainty that is, in particular, not out to get us. And also, it's useful to think about uncertainty that is out to get us, but I don't know how much we'll get into that here. And so we're going to need probability in the context of abstract toy models that help us kind of distill what's going on. In practice, when we're actually doing things, there are times where we're also going to invoke randomization and things like that. But you don't really need a lot of class level stuff to understand, like in terms of what you learn in courses, to understand the idea of like shuffling things. So operationally, the probability use might be less. It also shows up in the computation of certain important things like expectations and the like. But we're going to assume you know this. You need to know the basics of machine learning generally. Why? Because we're building on it. We're a specialized approach to machine learning. So what are the courses that hit the relevant ideas? Again, scene A, scene B, 189, or stat 154. Yeah.
Would 188?
No. Good question, but no. So if you mastered the material here, that plus 188 might do it. sort of the facility of thought that we're going to count on. But by itself, it won't. And then finally, you need to have some sense of if the only approach to information processing you've seen is by procedural program, right, where you have if-thens, right, that's kind of the basic thing that you do, you're going to feel a little bit lost in terms of what's going on. You have to have at least a basic exposure to analog information processing. This you can pick up pretty fast. Some people don't find it a challenge, but some people do kind of really wrestle with kind of understanding how you can have information processed in an analog way. This is definitely covered in Week 16b, or many of you have had in a physics class. Especially the concept of filtering. The key thing is the idea of filtering. Because in a way, everything we're going to talk about is like a giant glorified convoluted filter. Right? So someone could make a meme, right, of Pokemon evolutions. You start with like a basic RC filter, and then like later is a deep net. Right? It definitely grows out. So this is the background that we're going to count. So I'll talk later about how actually intellectually diverse the field of deep learning is. But any one course can't fully teach it from all the diverse perspectives that one can understand it. We're going to try to take advantage of our comparative advantage of sitting in a top research program and try to engage with it leveraging these tools. There are alternative tinkering ways to engage with the subject, which are also valid and provide great insight. That's not what this class is about. We're going to try to help you this way. So there's this really great XKCD comic, right, about machine learning, which I thought is just really, really nice in describing how things feel at times. So in this picture, people can read it, it says, what it feels like is you have this huge stack of linear algebra that you like shove data into and you shake it until it works. And this is, to some extent true of how it will feel. We hope the linear algebra and things will also be supporting some kind of building of intuition. But as I said at the beginning, we just don't understand this stuff that well. And we're going to be muddling through anyway. And so, at times, we're going to feel, and just that is this engineering or is this alchemy? Okay? In fact, before teaching this class, I actually went and I talked to lots of people in various big companies in deep learning groups. And I said, I'm teaching the class. Is there any particular thing you want, that you think would benefit people? I talked to other faculty as well. And you will not believe the number of times people have brought up this. This subject feels like alchemy. So let's acknowledge it, right? We're going to try to convey stuff from a scientific engineering point of view. But I want to, let's explore this parallel a little bit for fun, but also just to understand. I'm going to erase this stuff. So here, I'll write alchemy. And here, we'll put deep learning. Let's see if we can understand some of these parallels. So, alchemy, you were searching for the elixir of life. Something that will grant immortality. What is the counterpart in deep learning? It's called artificial general intelligence. a search for a super intelligent artificial entity. It's kind of like occupies the same kind of elixir of life kind of quest for motivating people, what they want to work on. In alchemy, you search for the philosopher's stone. You know, a mystic object that you can construct that will turn lead into gold. In deep learning practice, people look for ways to transmute unstructured data into dollars. Where there's like, build deep learning system, question mark, profit. In alchemy, people try to do things that would let them communicate with the dead. People try to do exactly this thing. In alchemy, people want to predict the future. In deep learning, people try to do exactly the same thing. In alchemy, people search for rich patrons. To fund their experiments. While promising them various things. In deep learning, people do exactly the same thing. So, that's like a bit of humor, right? But I want to say something in praise of alchemy. You might not have heard praise of alchemy, right? People usually think of alchemy as, oh, you know, horrible stuff that used to happen. And how could people like Newton and so on get mixed up with all this, right? But I want to say something very much in praise of alchemy. What alchemy did was it had an aesthetic. The aesthetic was you draw on ideas from anywhere and you try to make stuff by doing actual experiments. In an era when human beings are always subject to the same core problem, and that's groupthink and fashion. That you think that what matters is making the other people happy. And alchemy, early on, by its embrace of experimentation and empiricism, actually paved the road for modern science by telling what matters is what actually happens in the world. You can say that something was inspired by the sun had a battle with a dragon spirit, and so you should mix these two things together. But then you had to actually mix the two things together and do the experiment. And deep learning shares that spirit of intellectual openness, of drawing ideas from everywhere, and not worrying about whether they make sense or not, which is actually quite powerful. And so the question we have is that alchemy led to chemistry and modern science. And so what is going to happen here? Okay? So we're going to take the attitude that, you know, it's fine. And we're going to embrace a little bit of some of the alchemy aesthetic, which is we'll talk about theory and we'll talk about general principles, but we're also going to tell you the basic principle that, you know, if you want to make something work, you probably should try what the other person did that kind of worked first and just see how that does. If you don't understand why, still try it, right? There's an element of, it might sometimes feel like superstition in deep learning practice. And it's not entirely not superstition. But when you try things out empirically, that's okay, right? And this is one of the shocking things, right? Just again, a comment that you should all be aware of, a bit of humility. People were building cathedrals before they understood F equals ma. And sometimes deep learning feels like that. And again, that's fine. So what I want to talk next is a little bit of engagement with the history of the subject. So here, before I do that, any sort of questions or comments? We can have more of a discussion online, but anyone have anything they think needs to be shared with the class on this? Yeah. People literally try to make bots where they take the full set of texts and written information of their deceased relatives and generate a chatbot that lets them talk to the dead. This is, I mean, I'm not joking. This is actually what people often try to do. They also try to extend life and promise the extension of life. The reason alchemy did all that was that's what it takes to get people to pay for stuff. I mean, I could have listed, figure out poisons to kill your enemies, right? I mean, but at some day, people have to pay for things. And so that doesn't change very much over 1,000 years, what drives people. I guess love potions too, I guess, but I don't know. So I want to talk a little bit about the history. So I'm taking some of these slides from Sergey, just to kind of acknowledge the history of the subject. A little bit of my own twist on it. So people think about, what is the history of learning? People say Turing talked about in the 1950 of how you could use learning to get to intelligence. Claude Shannon as well, and a lot of people, Norbert Wiener in cybernetics, all talked about how learning could do this. 1943, you had McCullough and Pitt's model of the neuron as a way of trying to understand learning in the brain. A lot of people will date machine learning and kind of neural nets in particular to 1957 with Rosenblatt's perceptron, which you might have heard about in other courses. But it's also important to remember that at the same time, you had LMS, least mean squared algorithms, developed in the context of adaptive signal processing and control. And this is actually a figure from a survey paper by one of the authors of the original paper of the circuit kind of perspective on the first adaptive neuron that was done. And so what you're seeing, what the subject is kind of grew up around making circuits that can learn and has a long, long history of doing this. And it also goes through waves. So there was a lot of excitement with these early circuits on what they can do, kind of. And then in 1969, Minsky and Papert published a book where they showed a counterexample that certain kinds of circuits couldn't learn certain kinds of things. And that caused a crash of enthusiasm. But that crash of enthusiasm was actually a crash in kind of the popular or one side of the field. In EE, control theory and adaptive signal processing just kept going, kept building on these ideas for a long time. So those ideas kept being built upon. And then you see in 1986, you have backprop coming up in the context of neural nets. But actually, backprop had been working in adaptive control and those areas for decades earlier. So a lot of this field, kind of backprop comes from the idea of dynamic programming applied to using chain rule and things like this to figure out how to compute gradients fast. But people have been working on it for a long time. At the same time period, my slides seem to be broken. People think about the modern wave of interest in deep learning kind of starting roughly 2006, but really having a huge burst in 2012, where you have AlexNet sort of outperforming everything. But a bit of a personal story for myself. Back, around this time, I'm dating myself actually. When I was a high school student, and one of the first things I was doing, kind of, there's a research lab nearby, was I was sitting around figuring out how to, use neural nets and backprop in the context of op-amp circuit to, achieve certain goals. So people were kind of, very hot on the field, but then it kind of crashed again. Right? There was another resurgence of neural nets and neuromorphic computing and things like this. And what brought it down was that other techniques became, on the compute of the day, able to do better, and those other techniques were actually understandable. So people like understandable things. Part of this is cultural. Just acknowledge some of the cultural aspects of it. That, the areas of control theory and adaptive signal processing, which were developing a lot of, the underlying ideas, they were also defined by certain key applications that kind of motivated the field. And in control was things like making sure airplanes fly. And that led to a culture of safety, that you should understand what's going on, right? And not just like, oh, well, I don't know why I did that, right? That's not okay. And so whenever there were techniques that had provable guarantees and you could understand, they were very attractive and kind of could supplant other ones. Adaptive signal processing grew up a lot around making sure that computer networks were able to, and phone networks were able to communicate properly. And the LMS algorithm that I mentioned was deployed to make sure that you could track communication on cables that were changing their properties and wireless communication channels. And again, people don't like it if stuff just doesn't work. So, but underneath, you had these ideas, and then at this time, deep networks and neural nets sort of come back. Why did they happen then? And here, it's important to recognize that, in a way, deep learning represents an intellectual triumph of coming together of so many other things that allow it to happen. So, I could list this on the board, but there's no point in sort of spending time talking about it in great detail, so let's talk. You had the continuous improvement of underlying devices in silicon, right? Moore's law, what you think about when you hear Moore's law. And so you had things like FinFETs, that our own dean, right, Professor Sue J. King Liu, right, she was one of the pioneers of, that were kind of developed in the late 90s and really started to be able to drive advances in actual computers and architecture, kind of around this time. So computers were just getting faster and faster and faster. You had advances in magnetic storage and memory technology that allowed you to store and keep all these large data sets. You had improvements in computer architecture that constantly kept moving the ball forward. And you had the advance of GPUs, right, which were a particular kind of architecture. But why did GPUs come about? It wasn't to support deep learning, right? It was to support Pixar and video games, right? So it was computer graphics that was driving many of the underlying markets for these things. Realizing that, linear algebra is really, really useful for lots of things, including adaptive signal processing, including graphics. And so you can make specialized hardware, DSP accelerators, and GPUs. You had the rise of data centers and associated networking technologies that made it possible to actually host these things. And you had all of the advances in, you might think it's been completely unrelated, but were incredibly seminal. You had advances in CMOS imaging, allowing you to make in silicon imagers, which then led to the boom in digital cameras, which then led to the boom of sharing photos, which then led to the creation of large data sets online of things like Flickr, which then were curated to make these data sets, which allowed the progress to happen in deep learning. all along the way, while this is happening, you had the underlying algorithmic advances that have been incubated and ways of thinking for decades in control and adaptive signal processing, and then another Berkeley connection in fuzzy logic, which really brought ideas that were then grew into things like softmax that we'll talk about later. Kind of thinking about things in an analog way as opposed to a digital way, moving beyond if-thens, which kind of were driving digital computation and the way you thought about programs. So all of these things came together with this acceleration that's coming from Moore's law, and effectively made it possible to make bigger and deeper networks and to train them. I want to acknowledge something else here, which is that I said it's actually all of EECS, kind of has contributed to this. You had contributions, critical contributions from programming language, and the idea of domain-specific languages and then domain-specific languages embedded in other languages, that then people put in the hard work to create frameworks like Caffe, which is a Berkeley thing, which then later grew and evolved into things like Torch, PyTorch, TensorFlow, and the like, which made it possible to have ordinary skill folks copy and paste code and get deep learning models to work and then be able to tweak them. So a course like this, offered before the advent of things like Caffe, and even a course like 189, offered before the advent of things like Caffe and PyTorch, we would have spent a lot of time kind of making sure that you all knew how to program these networks from scratch. Take a paper, start with empty code, nothing, and code it up from scratch. That skill is no longer that important because of the power of these frameworks. So we're going to take advantage of that and not emphasize that as. So all of these things came together to make deep learning happen. And behind it is also, this spirit from alchemy of try stuff, get it to work. It's cool. Don't allow people, alchemy, let people who come from the trades, right, craftspeople, to contribute and engage with the subject, as opposed to being restricted to people, who are very scholarly. So that's also a part of it. Now, all that being said, there's one more intellectual component that I'm going to talk about, and it's going to form the focus of the class, is what happened around here in 2006, 2012, was there was a shift in how people thought about the design of the circuits for deep learning. Before, there was a lot of emphasis on thinking about neural nets as universal function approximators. We're going to engage with that, but thinking about them as kind of being able to approximate any function. And what shifted was a focus to something that we call inductive bias, which is that we want to learn particular kinds of functions well. And that shift of starting to think more seriously about inductive bias is what allowed people to move from convnets and keep going. And we'll talk a lot more about that in the class. Okay, so I usually don't like talking about all this history stuff and why now, but a lot of people like talking about it. You can also talk about the brain side. Many people believe that deep learning owes a great deal of intellectual debt and inspiration to studies of the brain. Other people think not so much. That studies of the brain is pretty complicated. We don't understand it very well. And while we can be inspired by aspects of it, we can be inspired by lots of other things too. So it's another source of inspiration, on par with the sun spirit had a fight with the dragon spirit, and so you should do this. But the important thing is we try stuff out. And there's lots, you take ideas from everywhere. Okay, so I'm out of time for today. So before I close, I'll just set up the story of what we're going to do next. So let me switch to my the website, so you have a sense of what to expect. 1 second. screens are like, I lost all my screens. Where did it go? Okay, whatever. So I'll say it out loud. Next lecture, what I'm going to do is I'm going to start engaging with some of the core doctrine of deep learning, which is take data, set up a loss function, optimize it, and understand what goes on. And I will also start talking about the core trade-offs that one is navigating. I'll try to set this up in a way that will be a brief review of material you've already seen in a machine learning class, and then we're going to challenge that. In particular, there is the idea of, so if you want to go and read something, go read about the bias variance trade-off, understand how people think about it, and then we're going to tell you why that's only part of the story, and you need to understand more. It turns out this improved conceptual understanding will help. After we do that, basically for a week, we're going to kind of go in and kind of resync you to the core underlying ideas. In discussion, however, on Wednesday, I hope you will actually start engaging with neural nets, starting in the first discussion. I don't want to have a lot of buildup of math before you can even start touching the subject. Hopefully, you'll engage with PyTorch. So on your computers, bring your computers to discussion. Make sure you have a working Python installation. Anaconda, install general packages. We'll post maybe some more details online. And then you can start engaging with it. We'll see if we can release the homework to you on Friday. Not promising anything, but if we can, tomorrow we'll give you a homework. If we can't, it'll be the next week. It's all good. And after that, we'll start talking about the following week. We'll talk about a survey of different kind of problems that deep learning can work on, different kind of give you a scope of the different kinds of architectures, different kinds of problems. And then we'll start going into it. Go into convnets, start talking about the details. In every lecture, once that starts happening, I will hope to have some maybe theoretical or conceptual interludes, kind of break up the pace of boring stuff and with other boring stuff, but different people find different things boring. So to keep everything engaged, and we'll just keep going in the class. Online, I will ask folks to participate in if there are things that you would like to see covered. We might be able to take some requests of balancing the topics a bit. But, we can only teach you what we know. So you might ask for something that we don't know how to teach you. OK, with that, I will stop.